Hi, everyone, and welcome to PyData Global. We're excited to have you join us. Feel free to use the chat to connect with fellow attendees and share your thoughts during this session. If you have any questions, please feel free to post them in the Q&A tab, and we'll address them at the end of the session. Now, it is my wonderful pleasure to introduce to you the presenter of the 30 minutes here, Robin Linacre. Robin is a data scientist at the UK Ministry of Justice and the lead author of Splinks, a Python library for record linkage and deduplication at scale. So, welcome, Robin, and take it over.
Thanks so much, Patricia. All right, great. So the talk today is about how to solve the problem of data deduplication. This is also sometimes known as entity resolution. So we're going to be using Splink, which is a Python library that's able to solve this problem quickly and accurately, even on large data sets. And the idea is that by the end of this talk, you should have everything you need to start linking and deduplicating your own data. So why do we care about this problem? Well, in my experience, pretty much every big organization has this problem. So you're just pretty likely to run into this at some point in your work. And it really occurs when data is collected about the same entity. That's often a person, but doesn't have to be. So that data is collected without a unique identifier. That can occur both within data sets, where we call it data deduplication, or across data sets, and there we would call it data linking. But in terms of how the problem is solved, there's actually not a real big distinction between the deduplication and the linking case. So here's an example. These three records all relate to somebody called Lucas Smith. And it's probably the same person, but you can see there are typos here. There's missing data. This person's moved house. So how can we know for sure? So crucially, a unique ID, such as maybe a social security number, has not been collected for these rows. So we lack a person ID that can tie these rows together. And without that, it's very difficult to perform even like the most basic analysis of this data set, because we can't even answer questions like how many people are in this data set. So in a nutshell, that's what this talk is about today. How can we use a predictive model to identify which rows are the same and therefore estimate a new person ID column? That's the thing that's lacking in the original data. At a very high level, let's take a look at how we're going to solve this problem. So the first step is going to be to create pairwise record comparisons. So for instance, we may compare the first record to the second record. And for each of these pairwise record comparisons, we're going to predict a match probability. That quantifies the likelihood that the two records pertain to the same person. Once we've got those pairwise predictions, we essentially have a graph data structure. Each input record is like a node in that graph, and the links between the nodes are the predicted match probabilities. And by solving out that graph, and essentially by finding which nodes are connected to other nodes, we can group records together into clusters, and each of those clusters then receives a person ID. So here, these three records connect to one another, and therefore they form a cluster. And so we could assign, say, person ID A to the three Lucas Smith records. And that all sounds pretty simple, right? So the rest of the talk is going to dig into how we can do this quickly and accurately, even on large data sets of millions of records. Okay, so just an overview of how the talk is organized today. I'm going to start by talking a bit about Splink and its key features. Then we'll delve a little bit deeper into how it works and how it achieves high accuracy. Then I'm going to run through a quick example of some actual Splink code, showing how we can use Splink to deduplicate a real data set. And finally, I'll just talk a little bit about how Splink has been used in the real world. So let's start by talking just about the key features of Splink. It's a free and open source data linkage library. Under the hood, it uses something called the Foleggi-Sunter model, which is often seen as a sort of best practice statistical approach to this problem. We'll come on to how that works in a bit. Splink was developed primarily due to the lack of free libraries that were capable of linking really big data sets. So there are some great alternative options for record linkage if you have maybe 10,000 records. If you have like 100,000, they start to get pretty slow. We had more like 100 million records. So basically in Splink, we're actually using a pretty similar methodology to some of these other libraries. We're just making it run much faster so that it can scale up to very large data sets. In terms of features, I think the key things are speed. So Splink is capable of linking 1 million records on a laptop in about a minute. Accuracy, we actually now add quite a few features to the sort of vanilla methodology that enables Splink to be more accurate than other similar approaches. Scalability. So one nice feature of how Splink works is that it offloads the sort of big data calculations to your chosen database backend. That could be Apache Spark, DuckDB, or we support several others. And as a result, it's very scalable. So several users, including ourselves, have used it to link over 100 million records. Unsupervised learning. So one of the really big challenges in record linkage is that it's just rare to have labeled data. And hence, supervised machine learning techniques aren't necessarily that useful. Splink uses unsupervised learning, so you don't need any training data. Interactive outputs. So we'll see in this talk that we put in a lot of effort to outputting sort of diagnostic charts and other dashboards so that users can truly understand what the model is doing and diagnose problems. And as somebody who works for government, this is particularly important because we want to avoid sort of the use of black box models for anything that can affect citizens' lives. Let's talk a bit about how Splink works. So at the core of Splink is the predictions it makes. That's given two records, like the two on this slide. How can we make a prediction of the likelihood that they're the same person? If we want this prediction to be accurate, we somehow need to kind of wring as much information out of these two records as possible and factor it all into our prediction. And I'd like to propose that there are like broadly three different categories of information that we could use here. And I'm highlighting this because often record linkage solutions maybe use only one or two of these sources of information. And in doing so, they're leaving accuracy on the table. So let's look at each of the three in turn. The first source of information is fuzzy matching. There are functions like Levenstein and Jarrett-Winkler that look at a pair of values, usually one column at a time, and output a similarity or a distance score. So for instance, the Levenstein function tells us how many characters are different. So in this case of Smith versus Smith with a Y, it's a 1 character difference. Or the Jarrett-Winkler will give us a similarity score on a scale of 0 to 1. And these are really useful functions. We'll definitely want to use them, but they're limited in that they only consider the two values in isolation. So let me give you an example to show why they're not everything. They would score a typo in the surname Smith the same as they would score a typo in the surname Linacre. But that doesn't feel right intuitively. So Smiths are obviously more common, Linacres are less common. So a fuzzy match on Linacre feels like in some sense it's more valuable than the fuzzy match on Smith. So that brings us to information source number 2. So information source number 2 can loosely be described as the term frequencies of the values in the data set. The idea here is that we need to take into account sort of coincidences. So how often do we observe the same value for different people purely by coincidence? So for example, the match on Smith is less informative than the match on Linacre because it's more common for just two random different people to share the surname Smith than it is for two people to share the surname Linacre. And this concept, it generalizes to fuzzy matches. So how often do we observe the coincidence that two people share the same name with a 1 character difference, for instance? So in summary, information source 2, it's about looking at what we can learn from the data set from outside the two records that we're looking at. So from the term frequencies in the data set as a whole. Finally, information source 3 is about data quality and how often values vary or are wrong amongst truly matching records. So for instance, consider these two dates of birth for Lucas. They differ in the month. There's a 1 character difference. It's either a 7 or a 1, so January or July. Now, suppose I told you that this data had been entered from handwritten records. You'd probably say, well, that kind of error is just to be expected. Somebody just mistook a 7 for a 1. And so despite the dates of birth technically being different, you'd probably say, well, this is actually positive evidence in favor of it being a match. But conversely, suppose I told you that the date of birth in this data set was extremely reliable, supposing maybe it had been automatically populated from people's driving licenses or something like that. In that case, you'd probably say, well, the differing dates of birth are actually pretty strong evidence against a match. So this information, which is like the evidence inherent in mismatches or the evidence inherent in the data quality of the data set, I think it's the most often forgotten when people are doing record linkage, and it's often just like completely discarded. So this leads us to a difficult question. How do we combine these three evidence sources in a principled way? So for instance, how do we weight an exact match on first name against a Levenstein distance of 1 on date of birth? Well, that's exactly what Splink is going to do for you by applying this Falaigi-Santa methodology. And in the methodology, we're going to be using the data itself to estimate the relative weights of these three different information sources. And that really just avoids the need for sort of humans to make arbitrary decisions about how important a match is on first name versus a match on surname, or like how important the difference is between a Levenstein score of 1 and a Levenstein score of 2. The point is that all of this needs to be combined into a single score, and we need to find an optimal way of doing this. So we're now going to have a quick look at Splink in action. I'm going to run through step by step the process of deduplicating a messy data set of people. I'm going to show a bit of code, but I'm not intending to go through it in any detail. So the example we're going to use is a data set of 50,000 rows of famous historical people, and that data set is built into Splink for convenience. For each record, we've corrupted it in various ways. So we've got a data deduplication problem. There are various nicknames, typos, missing data, and so on. So on this slide, we've just got the first 5 records. The first thing we should always do when doing predictive analysis of any kind really is to understand the data. And in Splink, we've just designed exploratory data analysis tools specifically tailored for record linkage. On this slide, I'm going to profile the first name column to take a look at this. And this figure tells me several things which are really relevant to data linking. The first is just that only 0.1% of values are null in this column, so that's useful. The second really important thing is that the column exhibits high skew. So there are loads of Williams and Johns in this data set, and then a long tail of more unusual names. I can quickly see a data quality issue. So the first name Sir, as in like Sir Humphrey, appears frequently here, probably shouldn't be there at all. And also when I look at the most uncommon values on the slide, there appears to be typos in the data. So I can see a misspelling of Paul, so I get some understanding of the data quality. So at this point, we may circle back and do some additional data cleaning, but for the sake of the talk, let's press on and assume we've analyzed all our columns. The next thing we need to do is decide which pairwise comparisons to generate. This is important because record linkage faces an n-squared problem. We usually can't compare every record to every other record because you would end up with just far too many comparisons. So even with this small data set, which is only 50,000 records, that would imply 2.5 billion record comparisons. And we're going to use a technique called blocking to reduce the number of records which are compared. The idea with blocking is to create a shorter list of possible matches, or another way of thinking about this is that blocking quickly rejects comparisons which are obviously non-matches. So from blocking, we want high recall, but we don't care too much about precision because these possible matches from blocking are going to go forward to the scoring process, and that's really where we decide whether they are in fact matches. Splink includes a bunch of tools to perform analysis of potential blocking rules, and this allows you to understand how they're going to perform in advance before going ahead and actually using them. And this is basically to prevent you from accidentally going ahead and creating 50 trillion record comparisons and blowing up your computer. So on this side, Splink is telling us that if we create all the comparisons where the first name is equal, it's going to generate about 16 million comparisons. That's obviously much more manageable than 2.5 billion. Generally, when you're using Splink, we would use a combination of blocking rules rather than just one. If you just blocked on first name, that enforces the condition that all of your comparisons match on first name. Hence, you'd probably be rejecting some valid matches where there was like a nickname in use or a spelling error in the first name. So you'd be rejecting those even before scoring them. So we usually use a set of blocking rules, and we've got some tools for analysis of this list of blocking rules. So here, Splink is telling us that the set of rules defined will create about 625,000 comparisons. But this chart is also telling me, I can see very quickly that the first rule is disproportionately responsible for lots of comparisons. So maybe we want to dig further a bit and understand that. So here we're looking at the specific values that are most responsible for creating comparisons for that first blocking rule, blocking on first name and surname. And we can immediately see in the table below that this is actually due to a data quality problem. This is telling me that the first name of Sir and the surname of Baronet is massively disproportionately responsible for creating record comparisons. It's creating like 300,000 of them. So at this stage, we'd probably loop back to our data cleaning, make sure we don't have any Sirs and Baronets and Lords and stuff in our first and surnames. But let's supposing we've done all that and proceed. So at this point, we've decided what record comparisons to create, but not how they're going to be scored. And this next part is really the meat of Splink, where we define how similarity should be measured for different columns so that we can train the corresponding match weights that are going to be used to make predictions. For example, for date of birth, one aspect of similarity may be typos, they may be one character apart, but another aspect of similarity may be temporal, like how far in time are they apart. In contrast, if we were looking at first name, we may ask something like whether the two names sound the same, even though they're spelled differently. Obviously, that wouldn't be meaningful for date of birth. So we need to go through in this way, column by column, defining a number of gradations of similarity, each of which will get its own match weights when we train the model. If you want to do this quickly, Splink has got a bunch of out-of-the-box settings for typical columns like date of birth, but you can actually customize these however you want. And that's one of the reasons that Splink is such a flexible tool and one of the reasons you can get a lot of accuracy out of it. This is going to be our completed settings object. This is like the config of Splink, and this defines how these comparisons are made for the similarity is defined for all our columns like name, date of birth, postcode, and so on. So at this point, we need to estimate those all-important match weights. And it's these match weights that capture the relative importance of, say, a fuzzy match on date of birth versus an exact match on occupation, or how important a mismatch on occupation is versus a mismatch on birthplace. So we're going to quickly take a look at how we estimate those match weights here. And I don't have time in the talk to talk like in loads of detail about model training. So I'm just going to show the code and then move on to how we interpret the results. But what this slide shows is the unsupervised training methodology. This is what you do if you don't have labeled data, and that's the more typical case. But Splink does also support supervised training of parameters if you're lucky enough to have decent training data. Right, so assuming we've run all that code and we've estimated our match weights, under the hood, these match weights are just a list of numbers. They're quite hard to interpret. But in Splink, we provide some nice graphical tools to help you understand and interpret them. So I'm going to start with this chart. It's a waterfall chart, and we can use this to visualize any single prediction made by Splink. And once we have a feel for this, I'll then show you the match weights chart, which summarizes the model as a whole. So let's take a look at this pair of records. It looks pretty much like a match, but note there's an error in the date of birth, and there are different representations of the birthplace. So let's see if the model predicts whether these are a match. So in the waterfall chart on the y-axis is match score. The higher we go, the more like matchy the records are. And that black horizontal line in the middle is a 50% match probability. So anywhere above that is likely to be a match. The waterfall chart is read from left to right and shows how the match score takes into account the various columns, name, date of birth, and so on. So right on the left, we're going to start with the Bayesian prior. And the way I like to think about this is we're sort of reaching into a box and it contains all the records in the data set. We're going to pull out 2 at random, but we haven't looked at them yet. We can imagine they're maybe in sealed envelopes. So the prior is a very small probability. It's the probability that these 2 random records are a match. And for this data set, it's about 1 in 9,000. That corresponds to a negative match rate of minus 13.1. But then in the next bar, we're going to open up the envelope and we're going to observe that the full name matches. So we update the prior with this new information. We apply the match weight for an exact match on full name, which is 11.4. And this pulls us upwards a long way so that our match probability increases. Next, we're going to observe that date of birth doesn't exactly match, but it is a fuzzy match. So we can see here it's got a match weight of 3.6. So that is evidence in favor of a match, but it's much weaker evidence than the full name match. So we add that on. And then further, we observe the exact match on postcode. Again, we have a very strong positive match rate here. It's been estimated at 12.3, so we go higher still. But then we observe this non-match on birthplace. So this is West Devon versus Devon. So since this information doesn't match, we've got a negative match rate here of minus 2.6. So that pulls us down in terms of match probability. Now, in reality, a human can actually see that these are kind of a fuzzy match, but this simple model has categorized them just as a non-match. Finally, here we've got a match on the occupation of politician. That's a relatively weak match rate here because the occupations in this data set are pretty broad categories. And actually, we can see here that further, there's a negative term frequency adjustment, which is made. What that's telling me is that politician is one of the more common occupations in this data set. So we end up with a match rate of 14.8, which corresponds to basically a pretty certain match. Okay, so hopefully that gives some way of showing that the predictions of these models are pretty intuitive. But these waterfall charts that I've just shown, they're only capable of showing the prediction for a specific pair of records. So there is a second chart, which we call the match weights chart, and that puts all of the match weights together. So it allows you to see the whole model. And this chart is capable of answering a much broader question, not just what predictions do we get from 2 specific records, but what match score could we get from any 2 records? And that's because the chart shows the match weights for all possible scenarios. So the blue arrows on this slide, they point to the match weights that we just used for the waterfall chart. So we've got the exact match on first name, the 1 character difference on date of birth, and so on. But what would happen if we had an exact match on date of birth rather than that 1 character difference? Well, in that case, we would have picked this match weight. So you can see just flicking between the two, we would have just chosen the higher match weight corresponding to the exact match on date of birth. So we can see here, we're still just going to add everything together. We would just pick a higher positive match rate here. So we would end up with a higher match probability as our prediction. So hopefully that just demonstrates these models are pretty easy to understand. There might be a lot of complex theory for how we train them and stuff, but at the end of the day, we're just adding up these match rates. We have a much wider variety of graphical outputs here, including some nice interactive dashboards. Sadly, we don't have time to look at them all today, but there's a link on this slide where you can look at a few more of them. So let's assume that we've looked at all these charts, we're happy with the model, we think it's doing what we expect. At this point, we can now do inference, so we can make pairwise predictions and then cluster them into our final estimated clusters. And that's what's shown on this slide. So remember I said at the start, the whole problem we're trying to solve is that we lack a unique identifier that ties these records together. And we can see that that's exactly what's solved by these outputs. So we've got this new estimated cluster column in red that ties together all of the variations on this Tom Chudley person so that they're all resolved into a single entity. So armed with this ID, it doesn't matter whether he's appearing in the same or different data sets, we can now join all our tables together using this new estimated cluster ID, safe in the knowledge that we're only going to count him once. At this point, you'd probably be interested in the accuracy of your model. So this is, again, a really big topic and we don't have much time, but Splink does have a variety of tools to help you out here. For instance, if you've got some labeled data, Splink can produce this accuracy dashboard that shows how false positives and false negatives change depending on what score threshold you use to accept matches. Okay, so that's it for the worked example. I just want to quickly cover use cases. So we've been working on Splink for almost 5 years now, and I think it's just really exceeded our expectations in terms of external users. It really started as a bit of an experiment into whether anybody would care. And we're now, I think we're over 9 million downloads now. In terms of our users, they span the public and private sectors and academia. So Splink is being used by the UK Office for National Statistics. It was used on the UK Census 2021, being used on the Interdepartmental Business Register here and other work. And it's also used by multiple other UK government departments. Internationally, we've seen some adoption, the German National Stats Institute, the European Medicines Agency, the Chilean Ministry of Health, and we've even had some really nice pull requests from the Australian Bureau of Stats. It's also been used in academia for peer review, research, and it seems to be fairly widely used in the private sector now. So as somebody whose career has benefited enormously from other people's open source work, I'm just really pleased that we can contribute something back here. Finally, I just want to point you in the direction of additional resources. So we've got a comprehensive documentation site on the link in the slide. I've also put these links in the resources tab. People's favorite part tends to be the interactive tutorial and examples. So we've got Google Colab links, so you can run Splink in your browser on that test data set nice and easily. You'll have seen throughout the presentation, there's little info boxes I put at the bottom of each slide that link off to the relevant part of the docs. There's actually a link to these slides themselves in the resources tab as well. I've also done some interactive explainers on the statistical theory behind Splink. Those are on my personal website, which is on this slide. So that's it for the talk. Thanks so much for listening today. I've actually been watching these kind of PyData talks for years, so it's really, really nice to do one myself. So just a big thank you to the organizers and for everyone watching today.
All right, thank you so much, Robin. We do have a couple of questions on the side for Q&A, and we have about 5 minutes left. If you'd like, I can go ahead and present these questions on the stage for you.
Yeah, brilliant. Thank you.
Okay, perfect. Here's the first one from Nathan. You see it okay?
Yeah, I'm just reading it. So also
Okay.
waiting available. Yes, there's various solutions to this, and this is where the custom comparisons come in. So you can define your scenarios, your like similarity scenarios, however you want. You actually use SQL expressions for that. So you can define custom categories or like gradations of similarity. So long as you can define using a SQL expression how to distinguish between these cases, then Splink will go ahead and estimate separate match weights for this. So maybe like a somewhat similar example here is in our data sets, we often get name inversions where they put the surname in the first name field and vice versa. If that is an issue in your data set, you can define like a name inversion comparison and you'll get an estimated match weight for that. But essentially, so long as you can define like almost like a case when condition that splits out the category that you're interested in, then Splink will estimate match weights for that for you.
All right, and it looks like we have one more question. I'll go ahead and show that on the stage for you.
Yeah, it actually goes further than that. So the question is, outside of deduplication, does Splink support merging, joining of two separate data frames? Yeah, so it actually supports an arbitrary like n data frames. In how we use it internally in Ministry of Justice is I think we've got upwards of 7 data sets now, which are all part of the same link and dedupe. But basically, the setting that you're looking for in Splink is link type. Then that's set to either dedupe only, which is deduplicating a single data set, link and dedupe, which is when you've got several data sets which themselves may contain duplicates that you also want to link. That's actually the case we have. And there's also a link only one where it will only create links between data sets, not within them. But basically, like the statistical theory and the model, the way the prediction works is actually identical. You can think about it as like the deduplication case and the linking case. The linking case is just if you stack your data frames horizontally on top of one another and then deduplicate them. That's an equivalent problem to linking.
All right. Well, thank you so much for your time here, Robin. We're going to go ahead and wrap up this session. If anyone has any additional questions, feel free to hop on our Discord channel to ask and continue the conversation, or we do have the lounge feature here on our AirMeet platform. But again, thank you so much for your time. It was an excellent presentation, and thank you all for attending PyData Global.
Thanks very much.